Thank you so much.
You good?
Cool.
Okay,
Yes.
so Eric has been a student in my lab for 9 years, and that's not because his PhD thesis took 9 years. He joined my lab when he was a freshman, and I think it's so awesome when students do that because they can stay in the lab in a really long time. And Eric's very first project, I think his second project, was to make a song on Baxter for kids called "The Grippers on the Robot." So like it went like this: the grippers on the robot go open and shut, open and shut, open and shut. The grippers on the robot go open and shut. All through the lab. There were about 4 verses, and we used it and still use it for the kids because it's very accessible, and it also feeds into his work in career robotics. So last spring, he taught the career robotics 101 with Sydney Skybutter, doing amazing work on the spot. Eric is one of those students that is just a joy and a gift, and I just come into the lab and feel so lucky every day to work with students like him. He's so good. You've got so many videos of robots. Every time a new robot comes into the lab, Eric is the one that makes it go. He's one of those people that sits next to the robot and makes it do amazing things. He works so hard, and he's a good citizen too. He's helping the students that are getting stuck or that are getting confused. Eric's the one that's like fixing their problems and giving them moral support as well as technical support, and not only empowering his own amazing research, but also empowering so many other people's amazing research in the lab. So it is with great happiness and also a little bit of sadness because you're going to leave, but mostly happiness and respect that I introduce Eric for his PhD thesis defense. Thank you.
Thank you. Thank you all for coming. I'm excited to talk about my research on abstraction for autonomous human-robot interaction. So fundamentally, my research is interested in developing algorithms and interfaces to get mobile manipulators into human society and help with general purpose tasks. And I really like this video from Willow Garage with the PR1 done over a decade ago, where there's a robot being teleoperated to do a wide variety of tasks like tidy a room, put away things, and do general living assistance. And I think what's really cool about this video is it shows that we've had quite the hardware to do some complicated things for a bit, but what's really lacking is the software and intelligence to enable robots to do this on their own. So to kind of understand why that's a hard problem, we can ask a question like, why can't we just use a large language model like ChatGPT to make a robot do every single task we want? And so we get some problems when we apply this to robots. So for example, if you ask ChatGPT to prepare breakfast, it's happy to generate a very detailed plan about what you should do. But there's some problems in here that it loves to reference high-level skills that you need to do. So it'll tell you to gather ingredients, prepare some eggs. Oh, yes. And to maybe put your bread into the toaster. And there's all these references to high-level actions that you should be doing to accomplish your goal. And I keep using the word high level because from a robot perspective, this is very high level. So at the lowest level of control, a robot just has to control its joints in order to move. So maybe at literally the lowest level for electric motors, it's sending electricity. And so this is really hard to deal with because of the fact that ChatGPT wants to tell us all these high level skills to do. So like gather things and put things away. And these are just not things that a robot has literally out of the box. Someone has to actually provide them to the robot so that it can then essentially coordinate its joints to achieve some of these effects. And actually, if you ask ChatGPT to, hey, try to tell me what to do for the robot joint, it refused to let you do that. And it just keeps on talking about high-level skills. So this isn't bad. High-level skills are good. And I'm going to actually propose we want that. And the reason I want to motivate why skills are useful is because if we give something like a task like clean room, and we have a task like prepare breakfast, we'll notice that we can actually have skills used across these different tasks. So if we know how to gather things, or if we know how to put things away, we can reuse those kind of behaviors in a lot of different settings. So the takeaway here are that skills are really useful because they make it easier to plan to achieve our goals, and they can be reused in different tasks. So let's make a wish list where we're going to put on things we want to do to get robots out into society, and let's add access to skills to that list. So you might ask, is that it? Is a roboticist's job just to program skills? And unfortunately, no. We're talking a lot about action here, but robots also have sensors, and there's some problems that we need to address there. So let's talk about that. So first, I'm going to say that I'm going to define a state as some collection of the low-level sensor data that the robot is receiving at time point. So for example, we have a spot that might have this eye-in-hand camera, so it can get visual data like RGB data, but it might also have some tactile data. So for example, here, there might be these contact points on the gripper where essentially it can detect how much force it's feeling at various contact points. And so essentially the robot gets this collection of multimodal high dimensional sensor data, and it has to reason about how it's going to achieve its goals. And this is really hard because there's a lot of distracting information in this state in the world. So if you ask it to do something like, can you grab the cup? Really, there's a lot of distractors here. So there's like random wires, and it's hard to kind of understand what this tactile ray is telling us. So ideally, the robot might be focusing on something like just that cup, or it might be focusing on specific parts of the contact array. And so what I'm going to suggest is what we really want are state abstractions or symbols, which formally are just probabilistic classifiers that can tell us whether a certain test is true or false. So for example, here I have a symbol represented like this funnel that can take in all the current sensor data and answer the specific question, is the cup nearby? And it can tell us the probability that that is true or false. And I should say that these kind of symbols are not necessarily sensitive to all the state variables. So for example, here, the image is black. Maybe the lights are off. Maybe the eye and hand camera is blocked because it's actually holding something. So it's not very useful to answer the question if it's holding an object, but we can look just at the tactile array, see that there's no force, and maybe determine that this symbol is currently false. And what's really cool is that what we can do is if we have a collection of symbols, then rather having to reason about this high dimensional low level sensor data, we can just apply our symbols to all of our sensor data and get a much more compact representation of the world that is just represented by the probabilities of symbols being true and false. And then what we can do is when we ask something like, can you grab the cup? Essentially, the robot can reason over these symbols directly. So maybe for grabbing the cup, there's some preconditions that are described about the state of the symbols, like that it needs to not be holding an object and the cup needs to be nearby. And the effect is that now it is holding a cup. So what I want to assert here is that we don't want random symbols or random tests, but symbols should specifically be representing the preconditions and effects of our skills. And what I'm going to say is that symbols are useful because they make it easier to plan to achieve our goals and that they can be reused in different tasks. So let's go back to that wish list and let's add access to symbols to that. And now you might ask, is that it? Do robots just need skills and symbols? And unfortunately, no, I'm not going to claim that I solved general purpose robotics in my PhD. And there's a lot of different problems that we're going to need to address to really get robots out into the world. But I'm going to focus on these two problems, how robots can get skills and symbols. And I think if we do that, we can make a lot of progress. So in general, I'm going to refer to the fact that skills and symbols have a similarity through the notion of abstraction. So skills are a form of action abstraction, and symbols are a form of state or perceptual abstraction. So when I refer to abstractions, I'm referring to both of these things. So a natural question to ask is, how do robots acquire skills and symbols? And what I'm going to say is that there are two sources of abstractions, from learning from the world and learning from humans. And actually, they have both pros and cons that are quite complementary to each other. So specifically, when we're talking about learning from humans, I'm going to focus on a particular class of interfaces for facilitating human-robot interaction. So specifically, virtual, augmented, and mixed reality interfaces. I'll talk about these more in detail later, but these are essentially head-mounted displays that can be used to augment the perception or the view of the user. And they normally have multimodal sensors like maybe IMUs and microphones. And the cool thing is that when we learn abstractions from humans, we get some nice pros. So for example, they're naturally interpretable abstractions because a human provided them, and they can help the robot more quickly solve the task than if it had to do it on its own. But there are some cons. There's a human in the loop, and that can be not scalable at large, so that's not great. And also, depending on the kind of abstractions and information, it's not easy necessarily for non-experts to provide the relevant information, and so we have to think deeply about what interface we're using. Now we can maybe what we should do also is have the robot instead learn its own set of abstractions just by interacting with the world. And so this is really nice. And I should say that when we're trying to learn skills and symbols from autonomous interaction, there's kind of a chicken and egg problem. So we normally do it in a back and forth process where either we have some set of skills and we try to learn symbols that characterize the precondition and effects, or we have some predefined symbols and we try to learn policies that try to have those effects in those certain conditions. And so learning from interacting with the world has its own benefits. No human input needed. So this is a very scalable approach, but these abstractions might not necessarily be interpretable, which is not great when they're interacting with humans, and they might be very costly for the robot to acquire, which is something we have to consider with real robot hardware. So I'm going to get to a question that's at the heart of my dissertation, which is to ask, how can robots effectively learn skills and symbols from interacting with the world and from learning from human teachers? And so actually, when we think about this, there's essentially two types of abstractions and two types of sources. So types of abstractions are skills and symbols, and the sources of abstractions are from the world and from the teachers. And so there's naturally 4 different problems here that we can try to address. And actually, my dissertation is broken up into chapters that try to address each of these problems, which in this talk, I will go through in sequence. So my first 2 chapters are about how robots can learn skills from interacting with the world. And due to time constraints, I can't talk about my second chapter. I'll just talk about the first one. Then my third chapter talks about how robots can learn symbols from interacting with the world. And my fourth chapter talks about how humans can actually teach robots those both types of abstractions. And so there's 4 different problems here, but ideally we would identify some sort of structure that can be used in all of our algorithms and interfaces across this problem space to help make everything more intuitive and efficient. And what I'm going to suggest is that we can be exploiting 3D spatial structure because it's something that's very readily available. It's on all the task distributions that a real robot would encounter, and it's something that our mixed reality interfaces can exploit effectively. And this leads me to the claim of my thesis, which is that my thesis statement is leveraging 3D spatial structures enables efficient robot skill and symbol learning, either via autonomous interaction or intuitive human teaching via mixed reality channels. So before we dive in, I do want to get clear what kind of input assumptions I'm going to be making across my works. So first off, I'm going to be assuming that we're in a fully observable environment, which just means that the state is based on some function of the collection of multimodal sensor data the robot currently receives. Next, I'm going to assume that we have an accurate kinodynamic model of the robot and access to a motion planner, which just means that when the robot needs to generate motions in free space and doesn't want to touch things, we can do that readily without any learning necessary. Next, I'm going to assume we have access to a semantic map of the environment. And by semantic map, what I mean is that the robot has the ability to estimate the 3D, have an estimate of the 3D scene geometries, either maybe as a point cloud or as a 3D voxel grid, and that the robot can actually localize itself in that map. And so this problem of making maps and localizing is referred to as SLAM, and we can readily do this today, especially in static environments. Next, I'm going to assume that there's a discrete number of objects, and this is actually something we can actually, and that we can estimate them. It's something we can do with off-the-shelf pre-trained visual models for task-agnostic segmentation and multi-view fusion approaches so that we can bring together sensor data to estimate the objects. And then also, I'll be specifically assuming that we can actually estimate the positions of those objects and maybe some other semantic attributes. So we can estimate the positions by having access to depth data, and we can estimate certain semantic attributes if we want to use a visual language model and have some pre-specified description of language descriptions of labels that we want to estimate about these objects. Okay, so now that we have an understanding of the input assumptions, I'm going to jump into my first work about learning skills from interacting with the world, which is this paper that we've been doing on the role of structure in manipulation skill learning. And what I first want to motivate is that manipulation is a really important problem because it's present in a lot of different tasks that a robot has to do. So this is actually an example of some videos that I did in collaboration with Mitsubishi, where we actually developed a novel VR interface to teleoperate this industrial robot arm. And as you can see, when a human is in the loop, we can do really complicated types of manipulation. So our goal is to actually get robots to be able to learn how to do these things on their own. And you might ask, why don't we just use our favorite deep reinforcement learning and favorite neural network to throw it at this problem and try to learn some manipulation skills from scratch? For example, we could have a policy parameterized by some vector theta, and then we could just execute that policy to collect a bunch of transition trajectories. And then we could use our favorite learning and optimization technique to optimize the parameters to the policy and maybe to the value function. And what happens in practice is when you actually try doing this, you'll notice that if the reward is very sparse and there's no help on exploration, essentially the robot, the best it can do is essentially flail its arm around until it happens to touch the object, at which point then it might be able to improve itself over time. But this is unsafe and not really great. And actually, to fully understand this, we designed some experiments in a simulator, Majoko, for this Panda robot arm with these 4 different manipulation tasks. So sliding a lever, sliding a knob, opening a lever, pulling a drawer, and opening a door. And what we can do is we can evaluate how the robot does, both in terms of success rate at completing this task and how often it actually violates certain safety constraints, such as hitting its joint limits. So we want this top row to have very high numbers and this bottom row to be very low. And so in this case where the robot is just using deep RL from scratch from a bunch of starting random poses, you can see in blue, we're completely failing, which is just like we saw in those videos. And this problem only becomes worse when we actually want to be manipulating a sequence of objects. So for example, here, the robot might want to pick something out of this black drawer, but in order to do that, it's got to open the drawer. In order to open the drawer, it happens to be blocked by this cabinet. So you got to first open the cabinet. So an intuitive idea is that rather than trying to treat this as one giant monolithic problem, we would decompose it into parts where we have maybe a skill for opening a drawer, a skill for opening a cabinet, and then some high-level task planner can decide, oh, you first need to open the cabinet and then you can open the drawer. And if these two skills were easily composable, then if we learned each individually, we can then follow that plan as desired. So this leads me to the work that we've been doing on developing a novel policy class for manipulating objects that we call composable interaction primitives, or chips for short. So before I formally define what a chip is, let me tell you why you want to use chips. So first off, chips are composable by construction, which means that if you train a bunch of chips for manipulating different classes of objects, it becomes very easy to rapidly compose them together, which is very useful for planning. Next, chips make object interaction safe and efficient. So by safe, I'm referring to the robot side of things. So we don't want the robot to rip off its grippers or fault out due to hitting joint limits. And by efficient, I mean how many times the robot has to interact with that object before it can successfully perform the task. And lastly, chips are modularized, which means that it's easy to design and add and remove different components. And so this is really attractive from both a scientific and engineering perspective. If we want to design a new kind of safety component or add a new way to evaluate sample efficiency or composability, we can keep most of the things fixed except one part and see how well it does, which is what we're going to be doing in this talk. So hopefully you look at these different properties and say, that's exactly what I would like my robot skills to have. Okay, then chips are for you. So what is a chip? Well, a chip is this 7-tuple here. So certain components are learned and other parts are hand specified. So the learned parts have a subscript C. So let's go through them. So first is the termination classifier beta, which just determines when the robot has successfully interacted with the object. So in the case of training a chip to open a microwave or close it, you can see that we'll be maybe estimating the joint angle of the revolute angle here. And when it gets closed, we're done with the task. So you can imagine this as essentially a predefined symbol for what effect we want the skill to have. And more importantly, what it's used for is to define the training signal for the actual policy. So I mentioned a policy, so let's jump to that. Pi, the interaction policy. So this is what's going to be the main part of a chip because it's what maps the low-level state to the actual action the robot will take to interact with the object. So in our experiments, the state is some collection of the current state of the object, the proprioceptive data of the robot, and some tactile data at the gripper. And our action space, we use something called variable impedance control and end effector space, which is a hybrid force position scheme where the robot can specify where it wants to put its hand and how much force we want to get there. And since we have a kinodynamic model of the robot, we can use this to translate it directly into joint velocities to move the arm. So just if you actually have just a termination classifier and a policy that is just this state and action space and train it, it's equivalent to doing deep RL from scratch. And so if we just have those two structured components of a chip, we get these results, which are not great. So what other components does a chip offer us? So we can look at the next part here, which is the initiation set classifier I. And its job is to propose 3D grasp poses on the object from which we want to run the policy pi from. And this is pretty intuitive, right? I mean, when we look at the video, it was mostly failing because it had to move. It wasn't even touching the object to begin with. So an intuition is the robot should first make contact with the object and then learn a policy for interaction. But this brings up a question. Even if we define an initiation set classifier so that we can propose grasps, how does the robot get there? And this gets back to my first input assumption, which is that with access to a kinodynamic model of the robot and access to a motion planner, we can just generate grasp poses and then generate obstacle-free motions to get to those poses. So that's how we're going to do that. And so this gets into the two other components of a chip, the H and T, which are just called the head and tail, which are just how we instantiate motion planning to get to the grasp poses. So when when you sample a grasp pose and you're moving there, that's called the head. And then when you're actually moving to the next chip, which is just the head for the next chip, we call it the tail. These are just the motion plans that we use. Okay, so the really important question here is, where does this initiation set classifier come from? So one option we can do is we can just use some task agnostic approach for generating grasp poses that put us in contact with the object. And ideally, it should have very few structural assumptions. So actually, here's a video from an algorithm that we use in our work called GPD that essentially all it requires is a point cloud of the object, and then it can just generate a huge number of grasp poses that have antipodal grasp poses for making contact with the object. So no structural assumptions, and we can just define the support for this classifier. Okay. And so if we do this, we're going to be kind of mixing motion planning with learned neural policies. And this is actually pretty similar to the literature on neurosymbolic task and motion planning. And so if you just kind of choose random grasp poses that are in contact with the object, you get this orange line, which is great. You actually start making a little success because you start touching the object. It becomes much easier when you're randomly moving your hand to maybe interact with the object. But we notice that these lines are still pretty unsafe, which is not great. Which leads us to the next part, sigma, which is the safety envelope. And so this is just essentially a wrapper that you put around your policy to try to enforce safety constraints. And I don't have time to get into the specifics of how we do it too much in our approach, but for the roboticists in the room, we use a mixture of null space control and potential fields to minimally try to enforce safety constraints without interfering with the primary output of the policy. But we hand specify these things, but if you prefer to learn sigma, you can imagine using something like residual policy learning. Okay, so what happens if we just put the safety envelope on top of the orange line? Well, we see that we're much safer, but we're not doing still great on task success rate. And to really understand why, you could probably understand that randomly sampling grasp poses that are in contact with the object is not the best solution because they're not all equal in how well they afford manipulation. So for example, here, there's this kind of free-floating handle, and we have two grasp poses that are technically, when closed, in contact with the object, but this one seems like it would slip off much more than the right one. So rather than just hand specifying this grasp pose, what we'd ideally do is actually be learning grasp poses in conjunction with a policy. And that would be really great. And actually learning grasp poses in order to enable a manipulation policy in the robotics literature is about learning affordances. Normally, this assumes that we have a fixed policy and then we're learning grasp poses. So we're in a much more challenging problem where we start with essentially contact grasp poses and a random policy, and we need to update them together. So I also don't have too much time to go into the deep details here, but we choose to go in this kind of iterative approach where we're going to fix our grasp poses and try to learn a policy, and then we update the policy, and then we fix the policy and try to learn grasp poses. And some of the ways that we try to bootstrap this is in two different ways. So one is to reference the fact that the robot isn't just some sort of free-floating hand in space, but it has a whole arm that it has to specify the joint configurations to get to that grasp pose. And actually, it's important to consider that because not all joint configurations are equal in how well they afford manipulation, even if they satisfy the same end effector constraint. So if we have a redundant arm with more than 6 degrees of freedom, our inverse kinematic solver might provide us with an infinite number of joint configurations that satisfy that end effector. And that makes it hard to learn good grasp poses because it could be random. It might not just be the best. So to address this, we introduce using the notion of a manipulability value, which essentially just takes in the size of the manipulability ellipsoid and how far the joint limits, the joint configurations to the joint limits to rank different IK solutions to make grasp pose learning easier. And so if you introduce this manipulability value and use it in your chip, you see that we get an even nicer improvement in terms of task success rate. So another thing that we can do is note that when we fix the policy and we're learning initiation set classifiers, we can actually not just treat this as some very generic sequential decision-making problem, but actually as a contextual bandit. And what's nice about that is we can use well-studied algorithms like upper confidence bounds to essentially explore and exploit over a discrete number of grasp poses. And this allows us to be much more efficient in terms of our learning. So when we integrate this in, we get this purple line that we call the full kind of chip structure that we instantiate. And you can see that we're doing very well in terms of task success rate and safety. And the real takeaway here is that we're getting over 95% success rate in less than 5% safety violations in just 100 training episodes. And we can really see this as clear in these kind of episodes here where we're going to be training a chip on the real robot to do this kind of task of opening a cabinet. So to kind of bootstrap this process, we've provided a demonstration to just help it along. But what we can see is that even from a couple of the first grasp poses, like 1 and 2, the robot can't really generalize the initial demonstration because it's out of distribution. The third one's okay. And just after 10 episodes of learning, the policy starts to improve and become much more robust. And then what's even really cool is that just after 30 episodes, now the policy that it's learned to refine can actually be generalized back to those initial grasp poses that it failed to do. And so now what we can do is we can just train a chip for opening a drawer, train a chip for opening a cabinet. We can train a chip to interact with any object. And then if some high-level task planner tells us what manipulation actions we want to do in a sequence, we can compose them for free via motion planning. Okay, so to summarize this work, we proposed a novel policy class for interacting with objects called composable interaction primitives, or chips for short. And the reason we want them is that chips are composable by construction, which is very useful for task planning. They make object interaction very safe and efficient, which is great. And they are highly modularized, so it's easy to slot in your own different types of implementations and understand how useful they are for impacting safety and task success rate. Okay, so that's about my first chapter on how robots can actually learn skills from interacting with the world. So let's move on to the next chapter on how robots can learn symbols from interacting with the world, which leads me into my work on synthesizing navigation abstractions for planning with portable manipulation skills. So I should say that solving this kind of problem of mobile manipulation is really important problem domain, because in practice, things are very spread out. So a robot's not only going to just have to manipulate objects, but it's going to have to navigate around to interact with them. So here we have this robot that's tasked with making coffee. And to help make this problem more tractable, we're going to assume we already have a set of manipulation skills provided to us. So for example, in this video, the robot has an action for picking up something, placing, pouring, closing a lid, pushing buttons, and these all just involve controlling the arm. And so you can think of this as essentially we've already trained a bunch of chips for a bunch of manipulation options, and now we just want to go to our mobile manipulator, give it some task, and have it plan for what we should do. And to understand what makes this problem still hard, even though we already have some skills, is to take a look at a motivating example where we have a robot in a kitchen, and we want to give it a goal like prepare some toast. And one of my input assumptions is that we already can create a semantic map of the environment. So we have the 3D scene geometries. We've identified some set of discrete objects that we care about, and maybe we've identified where they are and some semantic attributes about them. So what do we need to do? First, the robot's going to have to pick up a knife. Why? So it can slice the bread. Okay, then it's got to put down that knife. Why? So it can pick up the bread. Why are we doing that? Because we got to put that into the toaster. Why are we doing that? Because we got to turn on the toaster. Why? Because it results in toast being made. Okay, so what kind of going through this example emphasizes is that the robot is executing very specific skills because their effects satisfy important preconditions that lead us to executing other skills that have the desired effects. And so this gets me back to just my first point, that in order to do kind of the right kind of planning and reasoning about how to sequence actions together to achieve a goal, the robot needs symbols that represent the precondition and effects of our skills. Okay, that's one problem that we're going to have to address, getting the right symbols. But there's another problem here that I want to address, which is that if we even focus on the pickup knife skill that we've trained for a chip, when the knife is in the bottom right part of this room, the robot is not able to interact with it yet because it's too far out of reach. So it's going to have to navigate somewhere to enable manipulation. So this is important to note. We're going to be focusing on how navigation is going to be supporting manipulation. So we do have to synthesize the relevant navigation behaviors to support a plan consisting of how we want to manipulate the world. So to do this, we propose a particular data structure that we call an action-oriented semantic map, or an AWESOME for short. Before I formally define what an AWESOME is, let me tell you why you'd want an AWESOME. So first off, AWESOMEs make symbol learning much more efficient for mobile manipulators. So in the kind of general approaches, we don't want our robots to be taking hours of interaction with the object till it can learn some set of symbols. We want it to be able to be much more efficient. That's really good for robot hardware. Next, AWESOMes can be used to synthesize requisite navigation behaviors for manipulation, given that we've already provided skills. And so if we have an AWESOME, what we can do is we can train a bunch of chips, for example, put them into a training environment for a mobile manipulator, let it acquire some set of symbols and abstractions. And then what we can do is we can put that mobile manipulator into a whole different environment, and very effectively, we can give it a goal. And with very little learning, it can essentially start generating plans to achieve that goal. So hopefully you hear those properties and go, that's exactly what I'd like my mobile manipulator to do. Okay, then AWESOMes are for you. So what is an AWESOME? Well, I should first mention here that we're going to be operating within a particular family of approaches for learning symbols that we'll generally call skills to symbol approaches. And I don't have time to go into details here of how they work. Happy to talk offline, but let me tell you at a high level what happens. So we're going to assume that we have a set of skills, specifically manipulation skills. We're going to execute those skills in our training environment to collect a bunch of transitions. And then you plug all those transitions into your skills to symbols algorithm. You pull this, you just kind of crank this giant thing, and out pops a bunch of symbols that allow you to characterize the precondition and effects of your skills. So for example, here we have this pick up knife skill, and it has a precondition where its symbols are saying your hand has to be empty and you have to be near the knife, and that the effect is your hand is no longer empty, you're holding a knife. Great. Okay. So the nice thing about this family of approaches is in a fully autonomous way for us to learn symbols, given that we have a set of skills. Awesome. But the downside is the fact that this is an extremely generic approach to learning symbols. You could literally apply this to any sequential decision-making process you can think of. And so it ends up when you apply this to real robots, it can take hours of interaction until we can actually acquire a set of symbols, which is just not appropriate for real robots. So as I've been saying throughout my talk, what I would like to do is try to exploit 3D spatial structure to make this symbol learning process much more efficient. So to understand how this is going to work, let's look at some symbols that were actually learned from the original skills of symbols approach. So here there was a robot experiment that was had a skill for opening cupboards, and you can see some of the learned symbols that describe the preconditions for it. So for example, there's a symbol 4 that says, oh, the cupboard needs to be closed before you can open it. And there's a symbol 1 that's sensitive to just where the robot is in the environment before it can execute the skill. And what's really interesting is that if you actually look across all the different kind of manipulation skills and that were done in this experiment, there's always this kind of symbol that's sensitive to where the robot is in the map in the preconditions. Why is that? Well, it gets back to what I started with, which is that like most robots, this mobile manipulator had limited reachability based on the pose of where it was. So for example, if it wanted to open this cabinet, but it was in front of the cooler, it first had to navigate to that cabinet in order to open it. And it couldn't just navigate somewhere near it, just somewhere within a couple meters. It had to navigate to the front side, not the left or the right or behind, but the front, because that's how the skill was designed. So what we're going to do is we're going to identify that there's a special family of symbols that are only sensitive to where the robot is in the map. And we're going to call those spatial symbols. And what we're going to be able to do is by identifying the fact that spatial symbols are going to be present in the precondition of our skills, we can leverage the spatial structure by biasing our symbol learning process to search for spatial symbols in the preconditions of our manipulation skills. So I don't have time to go into the details of the kind of structural assumptions here, but the main high level idea is we suggest a new algorithm called spatially aware skills and symbols that has the same exact inputs and outputs as the original algorithm. Except the difference is that it is much more sample efficient when learning symbols for mobile manipulators. So you can see here, I mentioned before we had that pick up knife, and there was a symbol near knife. That's a spatial symbol. And I don't have too much time to go into the experimental results. Happy to talk offline, but essentially we compare our spatially aware approach to other state-of-the-art approaches for learning symbols given a set of skills. So here on the x-axis, we have the number of samples of times the robot interacted with the environment. And then it can plug that into the skills and symbols approach, whichever one it's using. And then we can try planning with those symbols and see how well we can actually plan. So we want this number to be up, ideally with few samples. So the blue is kind of a state-of-the-art approach, and the orange is ours. And what you can see is that by leveraging the spatial structure, we learn symbols much more efficiently. Okay, there's another thing here, which is pretty cool, is the fact that we're identifying spatial symbols are something that will be present and something we want to identify. We can go one step further to even make symbols better in terms of transferability, so that if we learn symbols in a training environment, we can plan in different environments. And this is what comes down to the idea that we're going to introduce object-centric spatial symbols. So to understand this, we have to do a little dive into spatial algebra. So specifically, let's assume that we want to pick up knife skill. So you can assume that if you want to represent the symbols for this, specifically the preconditions, you might have this spatial symbol that says you need to be in this little red region here. So the robot's got to navigate. Now, what happens when the knife moves to a different part of the map? This red region is no longer useful. It's not good for the robot. And so it's going to have to create a whole new spatial symbol for where to represent where it needs to be to manipulate that object. And we would expect this would be present not only in kitchens or one standard environment, objects move around, but when you go to a whole new kitchen, it's just not clear that like these symbols would at all make sense in terms of defining these symbols in a global map frame. So here, what I mean by global map frame is that when I say a position orientation is defined relative to an origin that's centered maybe in the bottom right here, and the orientation is defined by these axes that represent the rotation of the frame. And so what we can say is that we have this spatial symbol defined in the world frame. But instead of defining our spatial symbol in the world frame, why don't we just define it in the knife frame? So instead, we have now the origin centered wherever the knife is centered at, and we can define some axes as long as we can estimate the orientation of that object. And then we can define our spatial symbol in that knife frame. So when we do this, we call it an object-centric spatial symbol. And so what's nice is that when the object actually moves, the distribution in the object-centric frame isn't different at all. Now, there might be certain geometries and constraints that are now in play. So now maybe the robot can't go to certain poses because there's obstacles in there. So we can superimpose those and account for that. But what's really nice is that as long as we know the pose of the knife in the map frame, and that's what we get from our semantic map, and we define our spatial symbol in the knife frame, then we can always transform our spatial symbol back into the map frame. And that's really important because when we want the robot to actually manipulate the object in some pose, we can just sample that pose in the map frame and use an off-the-shelf path planner to synthesize the requisite navigation behavior to support manipulation. So I'm not going to go into the details, but we did some experiments to show object-centric spatial symbols are great for transferability. Here's an actually learned object-centric spatial symbol for interacting with this toaster here, where we've superimposed it back into the world frame. So this is a heat map where we've trained a Gaussian process. So yellow means more likely, purple is less likely. Happy to talk about that more offline. But the nice thing is now if the toaster moves around or we go to a different environment, we can just port that symbol without any initial learning necessary. So now I can finally introduce what an awesome is, since we understand what spatial symbols are. So an awesome is, as you can infer, a type of semantic map, which means that we have some estimate of the 3D scene geometries, and we know where a bunch of objects are. But the action component is that we also have a collection of spatial symbols for supporting a collection of manipulation skills. And so for example, here we have a semantic map, but we also have two skills, open microwave and toggle stove. And so with an awesome, when we want to open the microwave, we can have a symbol that we can sample from that gives us the poses we need to be in to manipulate the object. So how do we actually construct an awesome? Okay, so what we do is we have some training environment where we have a semantic map already made, and we have some manipulation skills that we can port to different environments, and we have some navigation skills that might be particular for this one. And what we can do is we can use our spatially aware skills as symbols approach to collect a bunch of transitions, plug them into our algorithm, pull that crank, and out pops a bunch of object-centric spatial symbols. And then we just call all the other symbols manipulation symbols. So now what you can do is you can go to your new environment, you can bring your manipulation skills, you can bring all the types of symbols, and then what you do is you make a semantic map of that new environment. And then in conjunction with the object-centric spatial symbols, you can construct an awesome. And then once you have an awesome, we can essentially be given a goal that's described using any subset of these symbols. And then we can use an off-the-shelf task and motion planner to generate a plan that involves the requisite navigation and manipulation behaviors to achieve that goal. So let me summarize what we've talked about. I've introduced an action-oriented semantic map, or an awesome for short. And what awesomes are really nice for is they make symbol learning much more efficient for mobile manipulators. And what's great is that awesomes can be used to synthesize the requisite navigation behaviors for manipulation. So we just need to train manipulation skills. And what that allows us to do is that we can just give our robot, we can train our robot in some training environment, give it some skills, it can then create the relevant symbols, and then we can go to a new environment, and without very much more additional learning, we can start rapidly planning for novel goals. Okay, so I've now talked about how we can learn symbols autonomously from interacting with the world. So I'm going to talk about my final chapter, which is how robots can actually learn skills and symbols from humans. And this gets me into work on building plannable representations with mixed reality. So I should say that I'm going to be using mixed reality as kind of a catch-all term for both virtual reality hardware, so like the HTC Vive or the Oculus Quest, and augmented reality hardware like Google Glasses or HoloLens. So the kind of similarity between all these things is that they are head-mounted displays that somehow augment the user's view. So in the case of VR, we render a completely synthetic world. In the case of augmented reality, we're superimposing 3D graphics on top of the real environment. And maybe they include spatially tracked hand controllers, so we know where their hand is. And there's maybe some additional sensors like IMUs and microphones. And the distinction between VR and AR is not really a hard binary. It's more like a spectrum, where, for example, when we want the human to be seeing the real world, we should maybe be using AR headsets. And when we want the human to be seeing a completely virtual world, we can just replace it and use the virtual reality stuff. So maybe a question here to ask is, when should I be using AR or VR for my human-robot interactions? And the answer is it kind of depends. So in the case where the human and robot are not co-located, but are remote, VR is a very applicable piece of hardware because we can just create a virtual world in which they are co-located. So for example, here, this is an interface that we developed in VR where we have this that allows us to do cool remote teleoperation. So here's a Baxter robot at MIT. There's a user here at Brown who's teleoperating the robot over 40 miles away. Now, augmented reality is used instead when the human and robot are co-located in the shared same space, because we don't want the user to be looking at some screen or synthetic world that's just not safe in practice for real robots. So what we can do is superimpose graphics onto the real world. So for example, here, this is work we did in developing a mixed reality interface where a robot is essentially generating motion plans. And then before it executes it, it can show essentially a ghost trajectory for where it's going to be. And a human can just simply walk around and intuitively understand, is that safe to do? And then tell the robot to execute it. So really, the goal of this work was to investigate how can mixed reality interfaces be used for enabling humans to teach abstractions to robots. And what we found is two things. So first, by using mixed reality, we can enable non-expert users to intuitively teach robots. And this is the case because normally the way it works is that some roboticist knows a programming language, has some notion of the abstractions they want the robot to have, and sit down and write it out. And that's just not accessible to everyone. And even if we make a graphical interface, using standard interfaces like keyboards, mice, and monitors, we found are not effective when you're trying to communicate spatial information. And that gets me to my next point. We can essentially design these things so that non-experts can easily communicate spatial information about skills and symbols. So what's really nice is that when we're using these kind of interfaces for teaching skills and symbols, what we can essentially have is a way for a human to enter into a novel environment with a robot, not really be an expert in robotics, but essentially decompose the task as they think. What are the relevant skills a robot should have? What are the relevant symbols they should have for reasoning? And directly communicate that to the robot to enable it to plan. And that's great. That's exactly what we want our interfaces to enable robots for humans to teach robots. So the question stands, how do we actually design a mixed reality interface to enable humans to teach robots skills and symbols? So to answer this question, we're going to have to somehow instantiate our abstractions so that we can map what our interface offers to something grounded to the types of abstractions. So we need to instantiate skills and symbols. So in this talk, what we're going to do is we're going to represent our skills as chips and our symbols, specifically the spatial representation components or the spatial symbols, as an awesome. Now, I should say and be upfront that the chip work did not actually exist before this paper did. We actually use a much more simplified action representation than what's offered in chips. But luckily, it's such a simplified action representation, and chips are so modular, they can actually map onto just a subset of what chips offer. So for the sake of this talk, I'm just going to act as if we're talking about chips. And awesomes were actually inspired by this work. And so the previous work I discussed actually formally defined how awesomes can be used for acquiring symbols autonomously. But in this original work, they were fully supplied by a human. So let me talk about how a human can use mixed reality to completely construct an awesome. So let's do a quick recall on what an awesome is. So an awesome is composed of two major things, a semantic map, and a semantic map itself is composed of two things, the 3D scene representation of the environment, and a notion of there being some discrete number of objects that are posed in that environment with some attributes. And then the action-oriented part of an awesome is that we have some spatial symbols, which essentially tell us the set of poses the robot needs to be in the environment, in order to enable execution of a collection of manipulation skills. So I'm not going to spend too much time about creating the 3D scene representations, because like I said at the beginning, robots can do it on its own. But it is worth noting that mixed reality headsets also need to do this kind of spatial mapping. So this is from the HoloLens, and it just creates these 3D maps in order to actually enable 3D graphics to be superimposed. So the reason I bring this up is because I think it's pretty cool that both robotics and mixed reality gets a mutually shared beneficial improvement when we improve our ability to do spatial awareness and reasoning. So pretty cool. But this is not our contribution. It's just something that comes with it. So let's talk about the more interesting part that we need to supply: information about what object classes are in the scene, where they are, and attributes about them. So we essentially offer an interface where users can define object classes and then instantiate objects of that class into the real world to build the semantic map. So for example, a class might consist of something like a kinematic mesh model, which is essentially a collection of meshes that are potentially articulated in that there's joints that constrain their motion. And users can create this either using a set of primitives, or they can use off-the-shelf assets from a store. And what they can do is they can essentially have a virtual representation that they can grab and move around in the world. And that pose in the world defines the global 3D pose of that object in the map frame. But in addition, we actually attach a local 3D frame to the origin of that mesh, which means that we have an object-centric frame. And then what we can do is we can define attributes for relevant for planning. And so some of these attributes, they can just be something like, is the object empty? But that doesn't really take use of the fact that we're using an MR headset. You could just type that in on a computer. But what's interesting is when you have attributes that are spatial, then they can be defined in the local 3D frame, and it's very easy to communicate those. So a more interesting attribute that you could communicate with MR is, for example, a 3D grass pose. And so when that's defined in the object frame, then when the object moves around, so does that pose, and we can reuse it. And as you can imagine, this is something that we're going to be using on the action side of things. First, let me finish the awesomes, because we want to talk about how we're going to supply spatial symbols. And I apologize in advance for the lack of stabilization on this video, since it's from a perspective of an MR headset. But essentially what we can do is instantiate a virtual representation of the robot that a user can drag around in place, and that defines in the poses in the object-centric frame where the robot needs to be in order to be posed and run its manipulation skills. Okay, so now we've talked about how a user can fully supply an awesome using an MR headset. So what about chips? Like I mentioned, we used a relatively simple representation in this particular paper. So all it maps onto is the initiation set classifier, which proposes 3D grass poses, and the interaction policy pi, which maps states to the low-level action space of the robot. So how do we use an MR headset to define I? Well, I kind of already mentioned it. Essentially, we're just going to have a user hand-specify grass poses and affordances for how to interact with that object. And since it's in an object-centric frame, whenever the object moves around or we instantiate new ones, we can reuse that classifier. Now, for the policy, we have a couple options. So on the left, we have a way where we essentially are inspired by this kind of approach where users can essentially create the grippers and essentially create a waypoint trajectory. And then we can just use an off-the-shelf motion planner to move between those waypoints. Also, if you want, and it's an articulated object, you can actually articulate the object in such a way, and then we can infer how the robot would need to move its hand to make that possible. And on the right, we are inspired by another more traditional approach for teleoperating robots, which is essentially we use the spatially tracked hand controller of the user to allow them to kind of do the task, and then the robot mimics that motion. And we find in practice that the left is a little better than the right approach, especially when the right approach is just replaying the trajectory. And one thing you might ask is, well, why are you just like having the human do that entirely? Why not just like use that to essentially as a supervised demonstration for behavioral cloning? And I'm going to talk a little about that more in my future work, but the goal of this was to try to have the human supply all the parts of the abstraction directly. Okay, so now we've talked about how a human can use a mixed reality interface to supply skills and symbols in the form of chips and awesomes. And for the sake of time, I'm not going to go too much into the experimental results here, but we designed this kind of household cleaning problem where we had novice users come in and they were tasked with these kind of different things like, throw away this bottle, turn on this light switch, close and turn on this faucet. And so you can just see some examples here of where the user is leveraging our interface to supply the relevant object information, attribute information, spatial symbols, initiation set classifier, and the policy. And you'll notice actually in this video that sometimes the robot messes up, and this could be due to a number of factors. So sometimes there's drift between the mixed reality headset map and the robot map, and sometimes it's just due to operator error. So we have a special way to enable something in the loop here so we can identify kind of what's going wrong and have the human properly supply that. Okay, so to summarize, what we've been discussing is how we can use mixed reality interfaces for teaching abstractions. And it really gets us two nice things. We can enable non-expert users to intuitively teach robots, and specifically what they can teach robots are the spatial information related to our abstractions, skills, and symbols. Okay, so that concludes my discussion on the fourth chapter about learning skills and symbols from humans. So I kind of want to recap everything we've talked about here today. I'm motivated that what I'm interested in is developing algorithms and interfaces to get mobile manipulators out into human-centered environments and perform planning for general purpose tasks. We discussed how what's really important for that is be able to have access to skills and symbols. And that where robots can acquire these things are either from interacting with the world on their own or from a human teacher, which really led us to these kind of four separate problems about the two types of abstractions from the two different sources, and how throughout my dissertation, we're trying to leverage 3D spatial structure to make our interfaces intuitive and our algorithms efficient. And that led me to my thesis statement, where I claimed that leveraging 3D spatial structures enables efficient robot skill and symbol learning, either via autonomous interaction or from intuitive human teaching via mixed reality channels. Great. So I then kind of walk through each part, where in the first section, we talk about how we can acquire these skills autonomously by interacting with the world. The next section, we talk about how the robot can acquire symbols on its own from interacting with the world. And finally, I talk about how we can have a human supply those abstractions directly from using a mixed reality interface. And I hope I've convinced you that although we're not solving general purpose robotics here, we're taking a step towards trying to cross off how we access skills and symbols, which I think is a really important step towards achieving that goal of getting mobile manipulators out into the real world and helping people. So I think a natural question to ask is, what's next? What would I like to do after my PhD? And there's several things that I would like to do. First off, I think some of my input assumptions are a little too strict for real environments and that they realistically have to be relaxed. So for example, I assume that we have a fully observable environment, which means that like we went around and built a semantic map before we even do symbol learning. And that's just not really practical in the real world. So we need a framework to figure out how we learn symbols in partially observable environments, which is going to require a little more on the scientific side to think about. Next, I mentioned that there's a discrete number of objects, which is really nice when things are kind of crisp and clean. But in the real world, this is kind of a question of how to even represent that. I mean, in this messy scene, how many objects are there? I don't really know. I mean, if you take a piece of cardboard and you rip it in half, you've made new ones. And if you take some flour and water and you mix it together, now it's kind of one, and then you spill it everywhere as a puddle an object. I don't really know. I think this is things that we really have to wrestle with and think about. Another thing that I'm really excited about is just generally improving and making better mixed reality interfaces. So I've been doing a lot of work with students at Brown. We've been investigating how we can develop cool VR and AR interfaces for the spot. So you can see some examples here where we're actually demonstrating different ways to teleoperate the spot and rendering the 3D point clouds in more efficient ways. So I think I'd be really excited to see what's the right way in the future of that. Lastly, one thing that I kind of would be open about is that my dissertation kind of feels like it's broken actually into two parts, where I've developed algorithms for learning skills and symbols and interfaces for teaching them. But in practice, I don't think this is just a one-shot thing. I think it should really be a back and forth, where a human initializes some skills and symbols for a robot. The robot then takes those and goes into the world, tries them out, figures what's right for it, maybe comes up with some new ones, some not interpretable, some are, visualize that and communicate it back to the human. And this process goes on iteratively. And actually, early on during my undergrad and a little during my PhD, we had done some work on exploring how we can actually develop algorithms to have humans and robots engage in dialogue and collaboration. And so I would love to go back and try to integrate this properly so that we can really have a collaborative skill to symbol learning process. Okay, so to kind of just say, I got to do a lot of work here over my time here at Brown, and I'm really thankful for all the cool collaborations I've gotten to do with everyone. So I didn't really get to talk about all the other works that I've been a part of. I mean, they're not necessarily really part of my own dissertation. Most of these works I'm not even the first author on, but I just want to show some cool videos that I'm really thankful I've gotten to work with people on. So I want to thank them. And specifically, I want to end my talk by just thanking my organizing committee. So Stephanie, George, James, Nick, thank you for being here. Really appreciate the support. Specifically, I really appreciate Stephanie and George, my co-advisors. They've been so important and fundamental for helping me become an independent researcher and have the ability to explore such a fun space of robotics. So I appreciate that. Something I'll truly always appreciate. I'd like to thank my family, my mom, my dads, my sister, my grandpa. Thank you so much for all your love and support. And finally, I'd like to thank all the friends and collaborators I've made along the way. When you spend enough years at one place, you'll make a lot of them. And they really have made this place super special for me. And I'll cherish the memories forever. So thank you so much. And I'll end my talk with having my thesis statement on the board. I'm happy to answer any questions. Thank you.
Very well done. Thank you, Eric. So we'll take questions from the room.
So there was a jump that you made between the initial explanation of chips and then having these kind of lifted chips that are parameterized by different objects, right? Like these skills that were dependent on, or also I guess symbols as well. That were like, you know, are you near the knife or pick up the knife? And I'm wondering if you can just speak a little bit about like how you could learn a general chip or a general symbol that could apply to many different objects or many different parameters. And
yes. So the chip is specifically, and I didn't get too much into this, but as I said, part of the state is something about the object state. And so we can parameterize that over a particular class of objects, but it's not necessarily designed for like applying one chip to like another class. So there's that parameterization included in the state. And then for skills, even though like our focus on the symbol or on the symbol learning process, we treat them as just like a particular skill. But the particular contribution of having spatially aware symbols can be applied to other approaches for symbol learning that deal with parameterized skills. So there is a family of work that actually deals with parameterized skills. So that can be parameterized over object classes. And so that fits in nicely. So I think that was a good point. That was just kind of an abstraction we made for this point. And actually in the original paper, actually, in the original experiments, we do operate in the symbol learning on different classes of objects. They're parameterized skills, but it becomes a much more harder problem when they're parameterized. So yeah, thank you. Yes.
So for the awesome work, you talked about learning symbols in an object-centric frame, which is important for something like opening a microwave where you need to be in front of it. And then you also have an example of picking up a knife where you don't need to be in front of it.
Mm-hmm.
And so I was curious if that affects the learning process or if that makes things more difficult, because I would think you would want a skill where, you know, if the knife is rotated, you know, that changes the frame. And so you want to be able to pick it up from any angle, but from a given example, you know, it's on a counter and you can actually only approach it from one angle. So you can't sort of learn all of it at once.
Yes. So what's really important here is if you have something like a pickup skill, you might intuitively know that like if there's no scene geometries like preventing you from interacting with it, that you could probably, depending on your skill, there's kind of like a ring around the object of places you can be. And in order to actually learn that kind of ring, you'd have to, in your training environment, randomize the pose of the knife in enough places in order to like experience the fact that like, oh, I can't like go to this pose. I can't interact with this object because there's geometry blocking me. It's because like fundamentally, I can't open a door from behind or like a cabinet from behind. So there's an important assumption here that in the training environments, you want to move your objects around such that we could experience all the poses that we want. And then the symbol is kind of optimistic in the sense that like ignoring scene geometries, we can capture where you could be to interact with the object. And then whenever the object's in a certain pose and we have the scene geometries, we essentially remove certain poses based on those geometric constraints.
Any Zoom questions?
Yes. Yeah, any Zoom questions?
Just shout it out, we'll hear you, I think.
I might have muted everyone. But please feel free to type any questions, but
Bertram has a question, Eric.
does he? Oh, is he? Oh, sorry. Let me unmute Bertram. Sorry. Or actually, you're not muted, I think, right?
I have just unmuted myself. I had the skill and the symbol power to do that. Fantastic work, Eric. I want to see what your thoughts are on this part of the wish list that you and I have worked a little bit on. That's how the next step of, for example, learning social norms might look like, and how the skills and symbols approach, and possibly even the 3D environment tricks that you used, which are really cool, how they could be leveraged for this, in some sense, even harder problem. There are no easy solutions here, but I'm curious how you could imagine that transition from what you have done, which seems to work really well, to these even more abstract challenges that norms would represent.
Yeah, no, thank you. That's a great question. And actually, I should emphasize that what we've been doing in all the approaches I've been doing here has been with a single agent. And so what's really nice is that I've been saying that you want symbols to characterize your set of skills, but those set of skills are the robot skills. So it gets a little more complicated when there's humans, and then you're trying to learn, you want to learn some symbols to think about, oh, there's these like social norms, and we want to learn symbols to characterize those. But like those should probably be defined with respect to the skills of the human. So now we're getting into like, what kind of skills does a human have? How do we model those skills? And so the symbol learning process becomes even harder when one agent is trying to characterize the symbols for some other agent skills that it can't even execute. So we're actually doing a lot of kind of like online learning where the robot gets to execute its own behaviors. So my first thinking is that we should really be thinking about how to generalize this kind of symbol learning process, and symbol specifically in the case where we're observing some human and we don't really have a direct explicit model of how they characterize their skills. I think that's a really open question. And I'd love to do some more work with people like you who think a lot about psychology and how people actually think about the world. I don't know too much about how humans break up spatial representations, so it'd be interesting to try to integrate that. I imagine they're not making point clouds and voxelized grids. So that would probably be important to characterize. And like, I don't think as a human, I think there's some origin of space that's arbitrary that we move, but like that's how robots normally characterize a position. So I'd want to probably start thinking about how humans characterize space and how to do this kind of symbol learning process in the context of the fact that we can't directly observe another agent's explicit set of skills.
Cool. Yeah, thanks. It's almost like you need a translation of the action repertoire of the robot and the action repertoire of humans and communities. And there might be some mismatches, and the robot might just not be able to represent, at least early on, learn some of these action spaces.
Yeah, no. I definitely agree with that. So yeah, I think that's a very open question, and I'm excited. I'd love to explore some of those questions since we've gotten to do so much cool work there.
About like certain skills, like it seems like maybe there's like or not, but if you kind of want cases where like the environment itself might change, like maybe there's different ways to open different doors. Like say for this one, like if you're any of these doors you kind of like leave it down, like but like say like a Tesla car door, you have to like pop it out first, and then on it. Like do you account for those kinds of cases?
So you could just try shoving that all into the policy and trying to make it so that I could generalize from different ones. But you could then also say that, like, depending on those different handles, you might want different grasp affordances. And so I think there could be an interesting question here where we could even use some sort of latent vector representation to define a space of different ways of modalities that an object class can be defined. And then based on that kind of latent representation, we could parameterize both the initiation set classifier and the policy. But you're getting into a very interesting question, which is that for within even a class of objects, or a particular class of objects, it's not necessarily unimodal. There might be multiple modalities to that object, and we'd have to characterize that. And I think that would get into some interesting perception questions, which perception is not necessarily my area of expertise, but I really hope I can work more with more computer vision experts and wrestle exactly with those questions. So I think that's a really good one. Yeah.
That if you're optimizing grasp position for, sorry, yeah, for like speed, for being able to move your arm in, more easily
Yes.
Is the like characterizing in which direction it can, characterizing whether it can move well, is it a generic classifier, or are you saying something like, I want to move well with respect to the next goal that I have, like the next, set of conditions?
Yeah, no, we're actually doing something kind of former. So happy to talk more offline about this because it gets a little deep into the mathematics, but there's something called the manipulability ellipsoid, which essentially says, given a configuration of the arm, how easy it is to move in different directions. So if my arm is fully extended, it's very hard for me to move it further in that direction, but it's very easy for me to move it this way. So like essentially when you're in a very nice part, your manipulability ellipsoid, the kind of perpendicular directions that define motion, if that's a very large volume, it means you can generically move in different directions. But you could imagine something more interesting, which is like, if I'm about to do a pulling action, does it really matter how much I can move my arm up and down if all I have to do is move it back and forth? And so that actually involves projecting that manipulability ellipsoid onto a lower dimensional manifold. That's not something that we do in our particular work, but I think that's something actually some people here at Brown are interested in exploring, and probably be the right way to properly think about that problem.
I had a similar thought with respect to cost. Is there does this generalize to a case where there might be multiple, there might be a sequence of skills you want to execute that have some overlap in their spatial?
Yes.
In the space that they are in, right? Where it might be you could imagine moving things from A to B where you want to be in, if ideally you're in between A and B, so you don't even between, right?
Yes.
Whereas I think that yours felt like you're sort of looking for the particular precondition for one skill. That's what you're optimizing for, and then you're not.
Yep. So our work is about characterizing the poses, but then a task planner's can be job to actually sample parameters in those poses, in those distributions to optimize an entire plan. So there's actually a lot of literature in what's normally referred to as like bi-level task and motion planning, where there's some high-level task planner trying to decide high-level actions like manipulate this, manipulate that. But then at the lower level, you have to choose parameters. So I treat obviously these are I'm saying these are classifiers, the symbols. You can sample from them when you just use a sampling approach like rejection sampling. And so we would refer to this as a kind of bi-level planner's job would be to maybe try to choose parameters for inside those classifiers that maximize our ability to reduce how much we have to move. And so that's not my particular contribution on the planner side. It's more producing the model of the world for a planner, but you're getting at the right exact questions that people in bi-level and like task and motion planning think about a lot.
Questions? More questions?
We do not have any remote questions.
I just wanted to give a comment. It was an excellent presentation, Eric. I loved it. You were great. Yeah, that's it. Yeah.
Thank you, Ifra. Thank you so much. I appreciate you being here so late. Thank you.
I wouldn't miss it. I wouldn't miss it.
Let's take our speaker. The celebration or consolation party is going to be upstairs on the 3rd floor. What? 4th floor. Okay, so everybody who's not faculty, I think, should head up here, and we'll just kick everybody out of the robot lab. So don't work on in the robot lab right now.
Thank you, everyone on Zoom. I really appreciate it. Thank you so much.
Love you.